left. So this is a function that, given a sorted array, increases, it returns the index of the first element that is greater than or equal to x in the array. So returns index I, where r sub I is greater than or equal to x, and it's really the first from the left index. So let's write out some examples. So if we have the array 0, 10, 20, 30, 40, and we pass in, let's say, 31, we're going to return 0, 1, 2, 3, 4. It will be inserted the fourth index. If we have that same array, but we input, but x is 51, then we actually return index 6. So note here we return an index that doesn't yet exist in the array, but it is just one more than the last index, aka index is the length of the array. And we'll do another case, if we have the same array but we insert, say, the value 0, then the first index from the left, that is this number, or greater than it, is the 0th index. So return 0, and let's say our number is -1. Well, the first number that is greater than or equal to this is actually, there is none. So do we return 0 here, or do we return -1? Let's go ask AI for the definition. So obviously you can't do this during an interview, but we're going to do it. So if you call bisect left on, does it return -1 or 0? Because there is no index where the value is greater than or equal to. Well, let's think about this. The first index where the value is greater than or equal to -1 is actually 0. So we answered our question. This would return 0. Let's do another base case. If we're just inserting into an empty array, I guess we return 0. Let's ask AI. If you call bisect left on an empty array with a value x, is the result 0 or -1? Okay, return 0. That's the insertion point. Okay, so here's another definition. Find the leftmost point where you could insert the value while keeping the sequence sorted. Okay. So let's see. Is this the same as... Oh. Okay, so we had the wrong definition. So yeah, bisect left is better instead of just turns the first insertion point where x should be inserted to maintain sorted. So this should be if current element exists. General definition for when the element exists or not is we find the leftmost position where you can Okay, so that's enough figuring out the test cases. Let's think, how can we solve this problem? Well, one way to solve this problem is using a loop invariant. So let's create a loop invariant where we create two variables. One is low, one is high, and these represent the bottom and the top of a range. And that range is going to signify possible value where the element x could be inserted. So if we look here, we currently have an array with indices from 0 to 5, but we could technically insert a value at space 6. So really the insertable range is from 0 to 6, which is the length of the array. So low/high represents the range that you can insert an element in. And what we're going to do is progressively exclude indices from this range that we figure out could not be the index that you should insert element at. And once, low and high are the same, there's only one element left. There's only one index left. So we return that remaining index, which would be low, would also be high, because they'd be the same value. So what we can do is essentially, while low and high are not the same number, aka while low is not less than high, we keep progressively excluding indices that we know cannot be the search range. So how do we figure out which part of the range to exclude? Well, let's do I guess we can use a sort of binary search here. So if we had an index that was the midpoint of low and high, would that give us any useful information? And the answer is yes. If we know, so if let's say we're right here and we pick the midpoint will be right here if you use integer division. So 20 is less than 31. So we know that 31 can only be inserted someplace to the right of 20. It can't be inserted, it could be, in theory, inserted, 1 to the right of 20. Couldn't be inserted at position 2, it couldn't be inserted at position 1 or 0, it has to be inserted at position 3 or higher. So if array of m is less than x, then we know our future searchable range needs to start at m plus 1. Otherwise, if array sub m is greater than or equal to x, well, what would we do then? So again, this is the midpoint. So let's make another scenario where we have this as a value. So let's make x 19. Well, we know that we need to insert position 2, but how does that work with our logic? Well, again, our midpoint is 20. Our midpoint is 20. 20 is greater than 19, so we're in our else clause. So if we're at 19 right here, we know that 19 is less than the midpoint. So the range that our return at x could be in is at most right here, because 20 is greater than 19, so that could be the most leftmost element. But in theory, there might be another element to the left of it. Maybe call that 19.5. So we just know somewhere between low and high is where we need to search now. Where high, the new high, is the midpoint. So I'm going to narrow the range to be this. And we just keep doing that over and over again until there's only one element left.